So my name is Vinod, and I work on the Hudi project. I've been with the project ever since its like creation at Uber, and through the open source, Uber open source, Apache incubation, and yeah, that's kind of like my brief intro here. Okay, I think we can get started. Let me share my screen. So yeah, I think I have like a slide. I want to start from some of the basics design principles and stuff, and take some high level questions. If I'm repeating stuff that you guys already know, like because in this crowd, I think you explored Hudi already. So if I'm telling stuff that you already know, just feel free to tell me, then I can like skip ahead. Um, but let's dive in. So high level, I think we can break our work like talk here into like sort of like three sections. We can keep it informal. You can interrupt me as whenever, and then we can cover things as we go. One is the high level design overview, like conceptually how we think about different design choices. What is Hudi, like overview, high level overviews. Then we can look into the right path, read path, the whole metadata, look at the code structure, some classes, entry points, like walk through existing configurations and things like that. And I also want to talk about like, upcoming work. So there are lots of large redesign work that's going on currently, which will, I think, fundamentally alter and reshape the project. So I just want to also like talk about those and then how this code may evolve to kind of support this. So for most of it, I think my slides are very thin. We'll like jump into IntelliJ or I can, we can do like a Jamboard thing, like it's some like whiteboard kind of thing, right? Like we can do these two to kind of talk through this session. Cool. So that does sound good to everyone. No concerns. Sounds good.
Yeah. So just quick question: will you make this PowerPoints or whatever slides available in the wiki page, or this is something that you just showing temporarily and just
yeah, if it's useful, I can. Some of these slides are borrowed, some are like handwritten.
okay.
Yeah, I don't mind if it's useful. I can make it available. So.
Okay, cool. Thank you.
But we are recording the session. We'll make the video available. So
nice. Thanks.
Okay. All right, awesome. So at a very high level, I think this diagram is borrowed from this page. And if you're not like haven't looked at this page, I encourage you to do that. This is, if you look at it, so this outlines all of the design principles of the project. We, as much as possible, we've also tried to explain the terms that we use everywhere. So if you look, what is an instant action, you'll see a definition for what that means and stuff like that. So it's like a good interactive way to kind of learn the jargons in the project, but also get a high level overview. But cutting back at a very high level, as you might know, what Hudi provides is essentially at the very, very, very core of it is you can upsert or delete a bunch of records at a given time. And then you are able, your queries can, query a snapshot of the table as of that given time, right? A snapshot basically gives you the latest committed value for every record in a table. And the one thing that sets Hudi apart from other systems that you have, which has always been a design goal from day one, is to support kind of, like how Pratyash mentioned, right? Many people do CDC from databases and write it into a data lake. We also want people to be able to CDC data from your data lake tables and build more chained kind of ETL data flows downstream. So we support like an incremental query, which can give you all the changes from a given time t-1 to a time t. So this you can use to build like incremental data pipelines, and like those we can go into these topics. But very high level, I think what Hudi provides is a way to write, upsert and commit data atomically, and then query a snapshot, and then this change string out of a data set which is stored on top of DFS. So through this talk, I will use DFS as a kind of a stand-in for HDFS, S3, GCP, or any of the Hadoop compatible file system implementations. So core design principles. So when we were designing Hudi, I think it's not an accident that we try to design it more like a database layer rather than like a big data format or something, because um, the only different because the problems are fundamentally the same. Like honestly, all we are trying to do was try to make it like MySQL. Like in any relational database, we can update data and read the redo log and get the change stream out, right? So we were like, mostly trying to approach it from like a database perspective, with while we pay attention to the fact that this is columnar. It's a columnar database, and during the right time, it has to behave like a OLTP database where you do like indexing. You want to quickly locate which files are dirtied and stuff. While on the read side, it is like it has to support columnar scans. So that is the kind of the unique specialization if you look at Hudi as a kind of a database problem. So second is we've always designed it for streaming writes and streaming reads. So by that, what I mean is if we new test Hudi tables, we write extra metadata around Hudi commit time, Hudi, like we have like a, like commit sequence numbers and things like that. So if you're familiar with the Google data flow model or Beam or any of like a Flink or any of these projects, I mean, most of them work with some sort of like a logical or arrival time, right? So even if you're like familiar with like Apache Kafka, your offsets basically provide you a way to tail a data set, right? So that you can do that at the record level. So that is kind of what we try to implement in Hudi to support our CDC is like we have record level metadata about when a particular record evolved, when was it written. This helps us to really build, really good incremental data streams, as opposed to having things file level, and you can only know which files changed. But within a file, depending on how you manage the files, some records could have been changed, some records could not have been changed. So we try to standardize all of that inside Hudi. And the other thing is, when we if you return taken a Hudi job and you try to write some data using Hudi, you might have noticed that the writer does a whole bunch of things, right? It is like so there is a reason for all of that. So we try to design Hudi as much as possible in a more self-managing way, because originally we were designing Hudi not for like 1-2 use cases, but right at the get-go, we had to land Hudi at Uber for say 1,000 tables, right? So we don't want to, for example, hand tune shuffle parallelism for every job. So I think and then we wanted to, for example, not sit and hand tune like file sizes and like, like in Spark, if you're writing spark.write.parquet, you often get the file sizing that's like an artifact of how many partitions that you choose, correct? We don't want to hand tune all of this for like 100,000 tables, right? So we decided, hey, look, like file sizing is like a really big deal. You get it right, you're saving so much cost on your queries. So let's actually absorb this hit on the right side and do as much as possible and make it self-managing in terms of, determining shuffle parallelism or sizing the files and things like that. So another thing is everything in Hudi is modeled as a log actually. So our again, this is a very different design, and in terms of how like big data frameworks have approached this problem in the past, they try to, if you look at Hive Metastore, or they try to move a table from a snapshot to another snapshot, which basically means if there are two concurrent operations, say for example, you have some operation which is adding files, some operation which is deleting files, there's no way to reconcile them. right? So how do databases do it? Like going back to MySQL, they have like a redo log, right? So everything in Hudi, the active timeline that you see in .hudi folder, that is actually like a log, which the instant times and the timestamps that you see in those files give you like an order, the absolute order in which certain events happened to a table. And again, we try to, we also extend this to data. So when data gets updated in merge and read, we'll like quickly cover all those things. But when data gets updated in merge and read, we try to log the data, not just produce like snapshots, right? So we embrace kind of log structured designs in a big way inside Hudi. That again is another key design difference between Hudi and any other systems out there. And the another thing is we actually embrace a key value model. So like just like Hudi commit time, we have a like a key that is in the data model itself. This helps us kind of do things like we can guarantee unique key constraints, right? Now that we have like a key, right? We so this is more like a unique key. We may not actually lay out the data based on the primary key like what MySQL may do, but yeah, overall, the model right now is more like a key value store kind of like interface, which everyone is very familiar with. Any questions so far?
Nope, pretty good. Thank you.
So with these, with my questions, I'll try to pause for like 5 seconds, and if I don't hear, I'll move on. But please stop me if I need to. So very high level, if you look at a table, how does it look, right? So how does it look all in Flush? So you can use some Spark job. I think we are working on Flink, and this need not be Spark data source. It can also be like the Hudi Delta Streamer tool, which kind of like gives you ability to CDC data directly in without writing code by yourself. So high level, a Hudi table sitting on top of DFS consists of three logical parts, right? So one is like an index. This can be external or within the Hudi data set. If you're using say HBase index versus so like the Bloom index, that's a difference. Then you actually have the data files, which actually store Parquet data and all your actual data. And then there is like metadata, correct? Which this is all in the .hudi folder. And then essentially we lay out the data in this way and then offer kind of these, if you look at snapshot and incremental queries, these are kind of like logical views of querying the data using these engines. That's why old times we used to call these things as views, but then I think it was confusing to some people where they were like actually it was like a logical concept, but it was being confused with actual views. So we just named it table like queries for now. But the idea here is we'll write just a manage like we'll just manage a file folder structure for your table and then expose different views based on the query type. And at a high level, we have two table types inside Hudi, as you might already know. And so first one is, I think, copy and write. And this is like an animation that I made a while ago. If you guys are familiar with it, we can quickly go. But high level, it shows what copy and write does, which is essentially it'll write Parquet files. If there are inserts or updates, it will just keep versioning the Parquet files. That is what it does. So here we insert A, B, C, D, E. So Hudi does its heuristic, say it divides it up into three files, file 0, 1, and 2. Then you do an update, two updates, you just like version the first two files. And then, you do another update and then an insert. It does the small file handling where it sees that, oh, file 2 probably can take one more record. And then like, instead of creating a new file for F, it actually, versions the file 2 as well. And then if you look at snapshot, at every commit, it's giving you the latest value. While incremental, if you're pulling incremental from time 0, you get everything. But if you pull incremental from time 1, you just get the records that you wrote that actually changed, the latest values. So we are also working on getting both the old and the new values. So it is like more standardized like database CDC tools. Any questions on this.
And the old files still stay, right?
Yes, the old files will stay. There is a cleaner process which will asynchronously clean up the old files after a certain time period. And by default, it is either you can configure cleaner commits retained, and it will retain those files that were touched in the last X commits, or it will, I think there's another config which isn't, or it's like 12 hours or something, it will keep it. The reason for the 12 hours is the minute you write, say, commit time 0, a Hive query can start here. It can be like a long running multi-hour query, right? But if you go and delete it now, that query will finally fail eventually, because Hive basically, it will plan and materialize these files into its plan, and then it is going to fail if you go and delete. So we essentially give it like enough time so that that even your longest running, say, Hive ETL or Spark ETL jobs can finish and doesn't fail because you delete the file underneath. Make sense?
I've seen that, like the asynchronous processes in some of the like conversations online also, but if you're just running Hudi as like a Spark dependency and using it to write or read, then Hudi itself can't run asynchronously, right? It can't like do processes on its own.
Yes. So okay. So the cleaning, for example, can run asynchronously when as you're writing data as well. Meaning, like, it is still running. If you have a Spark job which is using Hudi to write data in, uh, some part of the there'll be like one thread which is from on the driver, which is kind of like kicking off the entire write process, like doing this versioning and committing new data and stuff, while there is like another thread which can be asynchronously in parallel trying to clean up old data.
And it'll keep the job alive until it finishes. It's not going to get killed.
Correct. Okay. So both of them will do its job and then come back. So by default, what we do is we commit and then we run cleaning and then we come out. So when you are doing data frame dot write dot Hudi blah blah blah, what it's doing is internally it is doing two things. One, it's doing all this commit business of actually writing the data. It'll perform the commit. Then it will also kick off like cleaning. It'll do like archival. There is like few other bookkeeping tasks that it will do synchronously before it returns back to you.
Got it. Thank you.
Cool. So merge and read. So merge and read is very different. If you take the same thing, so the key difference here is instead of versioning the problem with copy and write was it's okay. The advantage is it's very, very simple, right? But like the problem is even if a single record changes within a Parquet file, you're rewriting the entire Parquet file, right? This can lead to very high write amplification for you, which is essentially saying if you change one byte, you're writing like 100 bytes on disk, right? So merge and read is more flexible in a sense that what we do is when we insert data, initially we write it as Parquet files. But whenever you try to update some data, instead of rewriting the entire Parquet file, we try to log the updates close to every file, essentially. So we kind of have this notion of like file groups. We try to bucket records, assign a key to a given file group at creation time, and we retain that till the end. So like now if you can see when you're updating D or A, instead of creating a new file with the change records, we just create a log and then write A prime, D prime in there. So whenever you're reading, now you have like three ways of reading data. You can either, your snapshot is the same guarantee. It's going to give you the latest value for the table. So it will merge the base file and the log files and then give you the latest value. Incremental just works like before, except it can read from the log instead of reading from the base, or it actually will read from a combination of the log and a base depending on the commit time. And read optimize is like a view that we kind of invented because sometimes people want actually don't care about the latest updates. They just want to run on pure columnar, you know, data. So read, that's why it gets its name as well, which is it's basically only doing columnar data. Essentially, you may miss some updates, right? And here as well, there is another background process, which is the compactor, which will ultimately, it has, you know, many different policies. Like some of the built-in policies that we have are compact the last n days, like, you know, compact the recent data more aggressively so that, you know, more of your recent data gets columnar query performance. Um, Compact the file groups with the biggest log files so that, you know, you can amortize the merge cost over time. You can even write one where you say, you know, okay, fully compact this, right? And compaction, once again, go tagging on to the previous question, it can be run synchronously in process with the writer. And it can also be run asynchronously. And as of like right now, there is a mode in the Delta Streamer tool where it will self-manage asynchronous compaction and writing by itself. We're also so we're also bringing the same capability to Spark streaming, kind of structured streaming sinks in 0.6. And that has already been tested. I think the code will probably land sometime this week or next week. Um, so that's high level how that works. So this compaction now gives you the ability to do a lot of different things. At least at Uber, the motivating use case for merge and read. I mean, merge and read was always designed from day one, but I think the real use case that pushed us to, hey, we need to move like most of our data from copy and write to merge and read was essentially GDPR and deletion related use cases. Sometimes what happens is you do a whole bunch of random updates on your upstream database for compliance or whatever purpose, right? Those updates trickle down in copy and write. Suddenly you have an ingestion pipeline where you are, you know, heavily rewriting the entire table, right? In merge and read, it allows you the way it allows you to actually like log all of this data very quickly and come out, while say you're using the compaction policy to just fully compact the last 7 days, for example, your ingestion job still runs in the same amount of time. So it's like these kinds of like random changes in update delete patterns or spikes in load have less impact on your kind of data ingestion pipelines. Again, like another thing that we like, these benefits kind of show up on large scale when you like, you know, have like hundreds of tables. Those are like the motivating kind of use cases for like something like merge. Any questions on this?
Just a quick question on this. Just curious in terms of, because we are a heavy copy and write, you know, kind of, you know, for the use case, that's what we are working on. But merge and read, I'm just curious in terms of the compaction, right? Like what is the best recommendations in terms of, you know, having asynchronous, you know, maybe like a cron job kind of fashions, you know, in terms of merging the data together? Like, is this something like utility tools are being provided already, or this is something, you know, we have to write a safe example, you know, a Spark job to, you know, to call the API and do something like that?
Yeah, good question. So right now I can summarize the support for compaction. So so like I mentioned, this is a good time to cut into like code, I guess. So if you look at the Hudi, you guys can see my IntelliJ, right?
Yes.
Okay, cool. So if you look at this, there is like a continuous mode. So this essentially what it will do is it will keep ingestion running and it will self-manage compaction for you asynchronously. This is something that we support if you're using Hudi Delta Streamer. If you're using Spark streaming, then this like a similar kind of you know support is coming where compaction and writing will be like a, share the long running Spark containers and do it yourself. Um, and it will be like fully self-managed by the Spark sync itself. If you really want to do it yourself, you need not write your own Spark job. You have two ways to do it. One is here is your, there is like a admin tool here, which basically, gives you some command line and like you can use this. Or the CLI has like just built-in commands for you to. There's a Hudi CLI which has built-in commands for, let me show you that as well. So you can play with this in our Docker setup. Like you can like, you can do things like this. You can say like compaction, schedule, override some configs if you want, and then you can do like rerun. There are also tools here that will help you unschedule a compaction, kind of like repair and kind of operate. So those kind of support tools are also here.
Great, this is helpful. Thank you.
I just wanted to add on to that. I think for existing Spark streaming, we do compaction, but it's an inline compaction, meaning like after the write, the compaction kicks off. The work that is going on in progress is to make it async, like how Delta Streamer does it.
Right. Sorry, yeah, that's a good point. So the one thing I did mention is some cases, right? I mean, some people express concerns about running like asynchronous compaction because, I mean, like general asynchronous processes are a little bit hard to reason about, right? And then, I mean, they're efficient, but you need to like understand them. There is like train your team, blah, blah, blah. So there is also by default, what we do today is inline compaction, which basically means we will write data just like cleaning, just like all these other processes. Before the thing returns to you, it's going to figure out whether it wants to run a compaction based on some criteria, whatever your policy is, right? It's going to essentially, there are configs which will trigger how frequently do you want to look at scheduling, whether you want to schedule compaction or not. And then there are, then every time, so for example, you want to schedule a compaction every 5 Delta commits, let's say. Every 5 commits, you want to see whether you want to compact data. I think that's the default. Then every 5 commits, it's going to basically call your like compaction strategy and say, okay, if you want to, do you think you have a compaction plan for me? And if there's a plan, then it'll, if it's in inline, we call it like inline compaction. It'll just like run the compaction as part of the regular writer process itself. This keeps it like very simple operationally. You don't have multiple processes. You don't have like a separate yarn queue for like compactor and things like that. But yeah, it definitely comes at a cost where it will add some more latency to your write. I can explain this setup more if there are questions.
So sorry, just to clarify, you mean inline compaction is more like a configuration based, like every 5 commits or 10 commits. So every time when you're doing the, I think this is applicable only for merge on read, right? So,
correct, it's only for merge on read, yes.
Yeah, so when you, let's say, for example, write 1 time, 2 times, 3 times, when you reach to the 5th time, and that's what you set as a configuration to do the compaction, then what you're saying is during the commit phase of committing the data into, the as the overall data into the log, then under the hood there's going to be another compaction kicked out to basically start compacting the overall with the Parquet file. But will the client returning back as asynchronous, or this is going to be like occupying that session and keep it going until it's finished?
Right. So I think this is the part that the last, forget the first half. If after you commit, like if you come here, if you're running inline compaction, it is going to hold that session and then it's not going to return back to you until it actually does the compaction. Meaning like actually merge the logs with like the base file and produce new base files, right? If you run async compaction, it is going to do the work of scheduling the compaction, which is to determine, actually just, get a plan for compaction out, and then it will return back to you, which will be like a lot cheaper than running the compaction itself.
Yeah, makes sense. Cool.
Sorry, I have a question here. So when you're doing cleaning or compaction, you're not affecting the commits, meaning that the point of time is still there, right?
Right. So we essentially, it's just like, yeah, so they're completely independent. So like we do the commit and then we refresh the active timeline essentially and see, okay, what do we need to clean now? What do we need to compact now?
Okay, thanks.
Okay, sounds good. So moving on, I think this will, let me see, I think presenting this probably will give you like a nice animation. Okay, so I think this is, I've been using this for a while, so apologies if you already seen this before. But logically, this is how things work, right? Like I mentioned, if you take a single partition on HDFS or DFS, you have the timeline which tracks all the actions that are happening to the table based on in time, right? And then within that you have these things called file groups. So what we call them as file groups inside Hudi, each like this 1, 2, 3, 4. There are four file groups now, and within each file group you can have a base file and a set of log files, and then maybe compaction runs produces these these green files here, right? Which now basically what you have is another slice of data, right? So we call these file slices. So for file group 1, what we would say is there are 2 file slices. The white ones are the older file slice, which had a base file and a bunch of like data committed. Wait, and no, I'm misreading that. Sorry, I apologize. So there are like say 2 file slices with the white base file, which is like the first, you know, file slice, and then compaction ran. It produced the green base file, which is the written by compaction at version 10.05. But asynchronously, still in parallel as compaction was running, writes can continue to happen at 10.06, 10.08, 10.09. So right now, file group 1 has 2 slices: the old one with just the base file, and a new one with the base file and a bunch of log files. If compaction were to run again, let's say on the state of this table, and then say produces, takes the green base file for file 1, all this log, it will merge and write, say, another base file on top of this, right? So the way to think about this is cleaner will keep deleting older file slices. Compaction will keep producing new file slices at the, and then that's sort of how you can see, right? Like that's where everything here is like very, you just try to keep logging, and then the cleaner just keeps cleaning up at the the head of the log, and then the compaction or writer keeps writing to the tail of the log, and that's how life rolls. And so you can have technically file groups, file slices without a base file with just like a log file. This way you can imagine writes can be much faster. Right now we support this only for when you're using the HBase index. And you can also have like a file group, file slice with just single base file, which is essentially what copy and write is, correct? And whenever you're reading something like a read optimized query, for example, at 10.10 will look at all the latest, essentially read optimized query will look at the latest file slice of every file group in a partition, and it'll just read the Parquet file. A snapshot query on this MOR table at 10.10 is going to read the latest file slice as base file if it has no log file. Just the log files, the latest file slice is log files if it doesn't have a base file. And then if it has a base and a log, it's going to merge and read the latest values. An incremental, essentially, we have the metadata. In every each of these metadata, we write what exact file was touched by that commit. So if you're looking for like 10.08 to 10.10, if you simply read this commit metadata, you now know which all files were like affected between this time, which all file groups were affected. We just go and essentially like read through. We also have metadata within these log blocks to be able to skip very quickly to the actual time. So we just read the portion of the log or the base that were affected in this time range, and then return those results back to you. That is in the flesh what we do. Any questions on this?
Just a quick question in terms of the file ID you were saying. Let's say, for example, if you have several versions of, let's say, for example, file ID 1, will the old file being, do you have, during the process of, having a new versions of file, sitting on top of the old one, is there any special treatments for the old files that you archived, in terms of Parquet file? And the reason I'm asking is because when I'm trying to, because I see, under the hood, like when Parquet, going through different versions, when I try to, just directly use Spark read the Parquets on, one of the old Parquet file directly, is saying, the Parquet file itself is not readable. So I'm just curious, is there any special treatments on the old files? Or,
No, if they should be, I mean, as long as you're not reading like, okay, the scenario that you mentioned can be happening if you are, say, reading an uncommitted file, right? Like, for example, if there was a delta commit at 10.11, and then if you spark.read the entire folder, right, you will also be reading. So maybe we are creating a file group 5, file ID 5, and that's like a partially written file, right? So that is what could cause that issue. Otherwise, there is no special treatment for old files per se. They should be perfectly queryable Parquet files. All we will do is enough time passes, and then cleaner will go and delete them. That's all.
You mean after, even for merge on read, or after the compaction of copy on write, or after compaction of merge on read, the historical Parquet file should be directly readable and kind of like being able to, let's say, if I'm directly reading Spark or read or Parquet, it should be automatically getting the result out of that Parquet file, right?
Yeah. The historical file should be readable as long as the cleaner is not deciding to delete it.
Gotcha. Okay, thank you.
So, just a quick question with that, because you mentioned the old files, once the cleaner cleans it, will get deleted. I don't know if you're going to discuss this later, but in terms of the incremental read, for figuring out what changed with the files that were already deleted, is that in a future slide, or is that something I should ask now?
It's not in a future. No, it kind of is, but yeah, I mean, we can that's fine. Like we can just hop there. It's fine to do this. I don't have like ton of slides. So this is kind of roughly the logic kind of for an incremental query. I don't know, my handwriting is, I don't know if it's that legible, but essentially there are three
just
steps.
make it a little bigger. Sorry.
Yeah. Let me try to do that.
Even if you just like drag one of the box, like one of the corners.
Yeah, actually, yeah, you're right. Like that's probably a better thing to do. Okay, cool. All right. This is probably better. Can you see it?
I'm good. I don't know about everyone else.
Okay, all right. Yeah, so high level, right? So how the incremental query planning works is, so first of all, we have this configuration which tells you how many commits you like. We try to match the amount of commits that you retain on the timeline to the amount of past versions that we retain. So what I'm trying to say is, if you say, okay, retain data for last 10 commits, which basically means any file version, any data that was written in the last 10 commits, those file slices will never be cleaned, right? So it's like a sliding window. So whenever you do the 11th commit, we will clean the first commits like data, right? So what this gives you for guarantee for incremental query is, you can go back within that window, think of it as Kafka retention, if you will, right? So you configure the retention for your commits, and then you within that range, we guarantee that the timeline, these files have the metadata, um, which will tell us essentially what files were changed within this time period. So then what we do is we determine the file groups affected in this commit range by reading this kind of Hudi metadata, right? And that's kind of like what I'm trying to do here. And generate the splits for these affected file slices. Then try to actually read those file slices and filter for only data that is in the affected time range. This is where again, like given the design of Hudi, we factored in like extra metadata fields. We can actually do this because for copy and write, as you can imagine, right? If you may have versioned a Parquet file in a given time range, but without this record level metadata, you don't know which record exactly changed. You just know that file got rewritten. Correct. So again, so we do one more predicate given we have this field and then get the change record. So that's how incremental query works. Did I answer your question or did I say something like?
Yes, I think the main part that answered me was you mentioned that there was a config that defined how long of a history that you want to maintain. I wasn't aware of that piece. So that's defaulted, I guess, to some value, and it's not, you can't do an incremental query from a prior point to that point in time.
Correct. I think it's defaulted to 10, I think.
Okay. What do you know what the config for that is?
Yeah, so it's called the cleaner retain commits.
Cleaner. Okay.
Yeah,
I can look it up in there.
Yeah. I know. I think I'm not very good with the exact name. Okay, yeah. I think this is 24. This is the thing.
Okay, so that's the piece that we want to be.
Yeah, retain commits. Just in configuration research and retain commits, you get.
Mm-hmm. Okay, thank you.
I'll also walk through the entire set of configs. Cool. So coming back, I think any other questions on the layout and the query plan, or any curious questions on why we chose to do this versus that and things like that?
Hey, Vinod, I have a quick question. I was wondering how, could you explain how Hudi decides the number of file groups, like on a insert or something like that?
Oh, yeah, this takes us into kind of file sizing.
Maybe later or something. I didn't.
That's fine. So what we do is, I think we use a bunch of heuristics here to do that. Let me try to explain this. This is also kind of like an important aspect of Hudi. So let me see if I can explain this more.
Vinod?
Yeah.
Sorry to interrupt. I have a follow-up question, what we were discussing some time back. So based on what Adam was asking, when the save time might be useful, save point might be useful if at all we want to store some comments in the past.
Yeah, correct. So yeah, something I forgot to mention, Adam, is like we also have like a feature called save point. I think it works. It's like battle tested for copy and write. I think it works for merge and read, but we need to like, if you're interested, we'll take a look and certify. So essentially what that will do is it will basically prevent the cleaner from cleaning up a past good version that you want to retain forever or something.
So you use it to mark a specific version?
Yeah. So at Uber, what we did was we know like say like some schema breakage or some bad data, whatever, these things happen, right? So we take like a save point, like a couple of points through the day. We retain it like we retain it's like an Apple time machine kind of thing. Like we retain like a save point for the last 2 days or something like that in the past. so that if something got messed up, we will rewind and then Hudi supports tools to roll back to that save point. So you can roll back the table. It's a destructive operation, obviously, right? So you roll it back, and then you can re-ingest the data with your fixes or whatever, and then recover the table back to a point in time. We do support that. Thanks, Shiva, for bringing it up.
That's for the rolling it back. That's for getting rid of it after, for cleaning it, or you're saying that's how to use it?
No, so that feature is designed for kind of like, disaster recovery, kind of data recovery kind of use cases.
Yeah. The reason I'm asking all this is that's kind of like why, that's a big reason of why I'm looking at using Hudi also. I guess I'll try to find documentation on this, but so I guess there's some sort of like Hudi command that needs to be run separate from like the Spark to mark those save points, and then and then you were saying that like after 2 days you get rid of them, but that's the cleaner takes care of that. That wouldn't be automatically taken care of.
Not 2 days. I think if you create a save point, it'll be there until you go and delete the save point.
Yeah, I meant you were saying that as an example. You guys were doing 2 days, like using a 2-day time frame. So then that there needs to be a matching like separate command from like all the Spark writing and reading stuff that'll say like this point in time we don't need anymore. But to use that save point, we would be using it the same way we use any incremental read with Hudi. Is that correct, or it's completely separate?
So okay, so I think let me try to understand let me try to answer one by one. So one.
Sorry, yeah, that's multiple questions.
Yeah, no worries. So there is like a save points command on the CLI. So this will help you like show save points, create save points, delete save points, and then you can also say, okay, I created a roll back my table to this save point.
Mm-hmm.
So this is how you like. This is like a kind of like an admin maintenance kind of thing. This is how you interact with save points, right? So the minute you take save points, cleaner will not delete the save pointed commit like instant times, basically. So you're gonna like retain the ability to roll your table back to that point for like going forward, essentially, right? And then in terms of incremental pull, yeah, technically you can say, give me the latest data after my save point, but it is not going to give you every version, correct? Because so let's say you took the save point here.
Like you're saying that if anything was added and then removed in the middle, that part will be missing.
Yeah, it won't be there. So if you took a save point here, right, and then like you did commits, right, for like 2 days. So the thing is, you're only going to retain the last 10, right? This is what's actually retained. Or 24 or whatever, something that is retained, correct? So these file slices corresponding to the save point will be there, but the things that are after won't be, right? Like these will be like cleaned up.
Mm-hmm.
So you can't get the entire change history. If you ask for it, what you will get is the latest kind of value from the last 10 that's all you will get. If you incrementally query from save point timestamp to now, you will get the latest value. That's all you will get.
Okay, but there is a way to revert directly to read data as of the save point.
Yeah, so but that will essentially be destructive. Essentially, what you're saying is, in a sense that it'll just like delete all of this.
Mm-hmm.
It'll like delete all these other versions and then restore the table to this point.
Got it. And that's one of the CLI commands. That's not one of the like read options, right?
Correct. It's not in the normal Spark data source or anything. It's like a CLI admin.
Got it. Thank you.
Just a quick follow-up on this. So in terms of the save points, can I understand that this is in parallel with all the historical versions you have with your particular Hudi table, and this is kind of like a more like a saved points that let's say, for example, if you want to do rollback or whatever, and if you screwed it up, then at least you can safely bring your state of your tables universe back to the save point that you care the most. Is that correct? So this is kind of in parallel with what you have in terms of the data.
Correct. That's correct.
Okay, gotcha. Thank you.
Yeah, this was like a very basic operational thing that we had to design to do these things. Cool. Right. Sorry. So like coming into file sizing. So here is how we try to decide file size, the file groups. So what we try to do is in copy and write, we have the commit metadata, right? So one of the things that we have in the commit metadata is for a given commit, we know the total records that we wrote, and we also know the total size of those files. So from this, we can derive an average record size. So what we do is essentially today, so whatever you're trying to write, when you're doing an upsert, we cache the data in memory before we write. We kind of determine how many records are going to what partition and whatnot. And we kind of do a bin packing algorithm, which will use the average size from this kind of heuristic and then try to write sort of well-sized Parquet files. So by default, I think we try to keep Parquet files at 100 MB. So the way we'll do it is updates are easy because you just version the Parquet file, correct? For inserts, as long as we think that by adding X records, this file can be brought to this optimal 100 MB size, target file size, we will try to send inserts. We will expand a existing small file as opposed to writing like a new file group. So that way, once you set an ideal optimal file size, you're not like, kind of like rewriting data all the time. Your queries always see, well-sized files, right? That's high level how sort of like, file sizing works. Do you have any follow-up before I explain more, or does anybody have more questions?
Just a quick follow-up question for this. I think I do remember I was quickly pick on the source code for this. So I think for the first time when you're running a table, then the heuristics information is not available. You're going to using the default size for each of the file group, which is 100 megabytes, right? And also I think this is some parameters tunable. But let's say, for example, let's say, for example, first when you initial writing the data into the file group, let's say is around like 20 megabytes. And then you say, at that time, you start having heuristic information is available. So what's going to be the decision going forward? Are you going to, say, okay, 20 megabytes, and then let's say, for example, 1 million, like a story, 100K records, and they wrap it up around, let's say, for example, 20K, bytes per record or something like that. And then you're going to, deciding this kind of, averaging size or whatever the file group size going forward. And the default 100 megabytes, per file not going to be in effect anymore, or there's some other things I'm missing. Do you understand my question?
Yeah, I got your concern.
Yeah.
So let me try to explain it in two scenarios. Whether you are using the bulk insert or the upsert API makes a large difference here. I'll try to explain both of them. I'll start with the upsert thing, which is kind of like what I think your initial, if I understood that correctly, what you're asking was, okay, very first time when I'm loading data, I obviously don't know any heuristics. I don't know the record size and or any of this, correct?
Yes.
So what do you do? So there's a configuration which has like you can override when we don't, it's called average. yeah, yeah, this guy. So this is what you can use. There is like, I think, yeah, I think with this basically has the things that we are, there's like a small file limit and a max file size or something. But yeah, high level, we'll use this default value. You can override that if you think your data is like going to be like much larger than this, right? So yeah, same problem. We did consider things like, hey, can we write a sample Parquet file and then throw it away if we don't have we haven't implemented those things. For now, there's a config which you can overwrite if this gets it like fundamentally wrong. That is for the absurd path, right? There is like a config that you can control the initial size. And from there on, we are hoping that this heuristic works, and it largely works. But yeah, over time, I'd like to redo this with a more separate stats DB table inside within Hudi itself. That's like a separate topic. But at least, did I answer your first question before I go to the bulk insert part?
Yes, yes, yes.
Okay. So the recommended way for this is how we did all the bulk initial loads at Uber when we were moving from like a non-Hudi to a Hudi world. So if you look at bulk insert today, it basically will do the following, right? It will read some data and then it will do a sort, a global sort. A lot of people complain about why are you sorting? So we are introducing new modes where it doesn't sort 0.6, but there is like a reason behind this. So when we are sorting, what we will sort by is we'll sort by the partition path and the record key in Hudi. So if you think about it, let's say how this will play out, right? So when you're having this initial bulk load, right? Once you sort by record key, let's say this data set has like, I don't know, 5 years of data or something like that, correct? And at least at Uber, okay, you can like the company grew very fast from say 2010 to now. It's almost 10 years now. So like to 10 years, right? So you will have, what you will see is, you'll see a lot of, when you sort like this, you'll see a lot of data, like you'll see something like this, right? The distribution will be something like this, right? There'll be like a lot of, then there'll be like a lot of 2013. So the data nicely kind of, yeah, and then when we write it, the way we write it is, we write partition, we write it in the sorted way. We can, we open a file, Parquet file, we write that Parquet file. As long as you're writing like bigger Parquet files, we also have ability inside Hudi. When we are writing a file, we can close if it reached a certain point. So in a sense, a lot of the small partitions which have very little data will mostly get one file, right? And if you're writing a lot of data sequentially for a given date, for a given partition path, we can like write nicely sized files, because our writer, the Hudi Parquet writer, can actually size files as well. Essentially, you can tell it. I can hop back into the code, but essentially it respects the whatever, like the 100 MB or something that you set, and it wraps say an S3 file system or a HDFS file system or whatever that you're underlying writing to, and it gets callbacks when the file has been flushed to 100 MB. So it will stop and then write the next file. It will stop and write the next file, right? So this whole technique, little trick that we use here, minimize the total amount of files that you write during an initial load while maintaining the file size. So we get like an optimal initial load, and then from there on, all of these other techniques that we do here will maintain the file sizes as we go. So that's like, I know this is like pretty dense, but that's the high level kind of why we even have like a separate bulk insert versus like a upsert and an insert.
I noticed, sorry.
No, go on. Like I was going to say, ask if that made any sense. Was it going too fast?
Makes sense for me now.
Makes sense. Thank you.
So I noticed that sometimes when I'm trying to do an initial load with a super small data set, for instance, like some sort of mapping data set, the bulk insert takes longer than a normal insert, but based on what you described with bulk insert, it doesn't seem like there's anything here that should be slower with a smaller data set.
Yeah, I mean, sort, whether you're sorting or not, is like sort itself is like when you run it on very, like, with limited memory in Spark and all, there's like bunch of things that can happen there, right?
Oh, there was no sort in the other one. I thought there was a sort with the upsert as well.
Yeah, so sort, so this upsert does shuffle data, correct? As well, but it will cache the data in memory. The code paths are kind of slightly different. I would really, for performance, I would really run it at like a, like a cluster and see, like, I'm not saying there won't be any, that there are no real problems. There might be problems, but those are more interesting to solve, like than trying to benchmark this on like a local machine. At least from what I've seen, some of the overheads that you see in a local box, though, don't even show up in a cluster because the bottlenecks move somewhere else. But if you ask me, all we do differently is if you're comparing this to spark.read.parquet.write.parquet, if you do that, we are doing an extra sort in bulk insert. And we are also converting from data frame to RDD to back to, like Parquet, right? So there is some format conversion there it's involved, which I think we have a PR out to kind of reduce that issue in 0.6 already. But those are the only two things. And with that, I think it should be similar. If you remove the sort is what I think throws people off because they compare spark.read.parquet to and just writing to Parquet to writing to Hudi, and then but this does this extra sort.
Okay, thanks.
But are you saying? Yeah, maybe you can take this offline, like a regular support channel.
Yeah.
Okay. All right. Coming back. Right. So I just want to I guess we went a little over, but that's okay. So yeah, overall, I think to just summary, right? Like this first part, this is like made me sound a little markety because it was done for like some talk, but the essence is still true. So the big goal here, if you can see, is we're trying to bring stream processing kind of like primitives, right? How do you write like a Flink streaming job, or like you tail data and then you have a update a state store, right? That is the kind of model that we want to kind of like bring to big data. And we feel we have the fundamentals here, which are very solid. We've invested in the right kind of like design for that purposes. And we hope that, we can bring more contributors on, actually truly build out a lot of these features together and make that a reality. That's kind of like why we are here, or at least personally, that's why I spend a lot of energy into the project. Yeah, just wanted to leave you guys with that. And we can go into like sort of like the code walk through, I think we touched pieces of that already, so I think we will save them sometime in the later sections. But so this is how the division of labor across different packages work. So Docker basically contains like this nice Dockerized demo setup that you may or may not have seen. If you have not seen, that's this guy. So it gives you essentially like a HDFS, a Hive server, and a Metastore, a Kafka broker, something to run your Spark jobs on, Zookeeper, like whatever. Right? It brings like an entire kind of big data setup in a Dockerized way, in which you can we use this even for development. It brings up Presto now as well, something that's probably not in that screenshot. It brings up this entire ecosystem. Helps us like test. We have integration tests running against the setup on every single commit. That's kind of like how we've been able to catch and maintain like a lot of these issues. The CLI is the CLI which we discussed, which is just like a whole bunch of these commands, and yeah, it's based on like Spring Bootstrap and Spring Shell, written a long time ago. And
could you zoom in your screen, please?
Okay.
It's a little small. Thanks.
Okay.
Yeah, thank you.
Cool. So yeah, Hudi client has all the writer code. Hudi common has the metadata, and the metadata is basically has to be shared by both the log format and all that, which is kind of shared by both the readers and the writers on the query side, are all in Hudi common. Examples. Hudi Hadoop MR basically depends on Hudi common alone, and then it's kind of like the Hudi reader kind of project, right? Where it has the input formats, which try to do filtering and like integrate into Hive and Spark SQL. And Hive Sync has code which will do, after you write a Hudi data set, how do you keep your Hive meta store in sync? It has like stuff to add partitions, add columns, alter the schema, things like that. And integ test is our integration test, which runs against the Docker environment. Hudi Spark is basically the spark.read.format.hudi. All of that's and write, all of that sits here. And a timeline service is something that, it's like something that we use on the driver internally by the writer. But the original goal for this project was kind of to have a meta server for Hudi timeline. Instead of listing the files or doing anything, we can actually, so maybe I can explain how that works, because this is probably something that we haven't covered very well outside. So the timeline server works like this. So you are familiar with the Hudi timeline, right? So, writes happen. There's a lot of like metadata that is written about actions that are happening. The Hudi timeline server basically reads this timeline, and then basically has a RocksDB instance in which it is building the latest snapshot of the table, like the metadata of the table, basically. So essentially, if you ask, hey, give me all the file groups for this partition, it has that information, right? And it supports basically a REST endpoints to kind of like provide this information to whoever wants. So you can basically ask for any of the information, like get all file groups, or get file slices, blah blah blah. Get my commits, get all the commits that happen, get all blah, blah, all of this, right? So initially, where we were going was, okay, we'll run this as a central thing in the project for sort of much like a Hive meta server. This is giving, we can even run like a Hive meta server embedded within this. That way, this is like a single thing that you deploy. Like, it uses Hive meta server to kind of manage the table schema and all of that, but it also has these other endpoints where you ask it for like the data set specific things, and it can actually tell you, right? This, you can imagine something like Airflow pinging this to say, okay, have commits happen? Okay, give me the commits. Okay, I'm going to trigger more workflows and things like that. We haven't really done so that timeline server has all that code. There is like a bundle. There's a bundle for this, which you can run the timeline server as a service. But what we do primarily today is we embed this whole thing in the Spark driver. So the Spark driver actually starts a version of this guy internally. And so, for example, when you're doing indexing and you're listing the table, and then when you're writing, you're doing something, it all gets cached here, this file system metadata. And then when you're doing the writing, you're just like, reusing this. This is turned on as of like 0.53. And all of that fun stuff sits here. And at least for something like Spark streaming, as we try to overcome these like indexing bottlenecks and move past to a world where we want to do streaming rights and 1 minute, like consistent 1 minute commits and things like that, you have to have something like this, so which is like backed by a REST endpoint and like a rocks db or something, like some fast scalable storage like this, where this, otherwise the whole like file system interaction can become a bottleneck. Again, like there's many ways to skin this cat. We are also looking at other ways in RFC 15, but this is something that's worth knowing in case any of you are interested in taking this idea to further. We had a poll before in the community, and people expressed interest in not having like a separate meta server. So we kind of like didn't build enough steam around running the timeline server on its own. But if we did today, it will solve so many other problems for everyone. Okay.
So, yeah, just curious. Do you have a issue number to track off, the description you just gave? And I'm just curious to read in some more details, because I don't think I have a lot of information for for this particular interesting features or issues.
Yeah.
Do you remember by any chance that you have a detailed descriptions written anywhere?
So there is an RFC which Balaji wrote, which describes the entire design. On the issue, it like we had a RFC like a discuss thread, and it never made it past that. So I don't know, but you can create one if you want. But yeah, this thing will talk about all of this. Like this is, I think, what we have right now. Yeah, you can file an issue. I'll be more than happy to like write a blurb of what I wrote here, and then we can go from there.
Awesome, thank you.
Cool. All right, coming back. Utilities. These are like Delta Streamer and all of these other cool tools that we have. And packaging is all these like Uber jar or Fat jar bundles that we hand out for Hive integration, Spark integration, Presto integration, and whatnot. Scripts has like a bunch of like release scripts, the CI scripts and stuff. So that's like the project structure, right? So code walkthrough. So I'll try to like cover like a basic path. Like I'll try to say how this is laid out and what are all the classes that affect these parts of things. Hopefully that's like a, like a useful thing. Again, you might have seen this, right? Like when you look at the base part, there's like data, which we kind of discussed before with the file groups and the layout and all of that. But in this slide, we'll spend a little bit more time understanding the metadata, the .hudi folder. So you can see these things, right? Which is like, you usually have like a timestamp. I've written 00111, but usually it's like a timestamp, right? And then like an action name and then a state. So everything goes from like requested, in flight to completed. And this is a log. Another common myth is we rename, which is we don't rename data. We don't rename any of this. We just like log request completed, and then we take it to completed. So anytime the queries see that a given instant is in a higher state, it will ignore the lower state. So for example, if you list this active timeline, you'll see a Delta commit with 3 files, right? But if you have the completed extension, which is like basically not having anything, then it is going to not, it knows that it's no longer an in-flight or no longer in requested. And this is what we call in the code as active timeline. So obviously this will grow in an unbounded way, right? If we don't do anything. So periodically we also like take, like, move some of these into like an archived folder. On HDFS, this really works very well because this is just using the same log format that we have for the data. So it'll like nicely write like log append files. But unfortunately, aside from Azure, none of these stores support S3 or GCP support appends. So this is like, I think you see a lot of small files under this. for the most part, except for CLI, nobody touches these things right now. But our hope is when we do RFC 15, we will actually bootstrap the table metadata by reading this. That is kind of like why we have this and what we plan to do with it. I'll describe those things as well in more detail. So temp, I think it has what we call as like marker files. I'll kind of like explain what they mean if you guys are curious about it. Or given that we have half an hour, I can also jump into the code. But very high level, I think when you're doing a write, you can so Spark essentially, let's say there is like a base file and you're trying to like do an update in copy and write where you're trying to version this file, right? You want to make A into A prime, let's say, file A into file, or let's say F to F prime, for not to confuse you guys. Then Spark can actually, with speculative execution or anything else, kick off any number of these like operations, right? And during commit time, it will only hand you one of them, like one task that succeeded. So our job here is two problems. One is, okay, on the query side right now we list, so these files shouldn't show up, right? If like this is what ultimately succeeded. This can be like partial files or whatever. We want to remove them. So whenever that's one problem. The second problem is, I mean, like if you keep this lying around with enough failures, your storage is like getting clogged with kind of these like useless files, right? Like even if we solved the query listing, the metadata problem, basically. So we want a mechanism to clean up all the dirty or like, all this like a partial thing. And generally for the hygiene of the data set, we only want to have files there which are valid data files, right? So what we do is, coming back quickly here, before we write any file into actual partition path, here in the data part, we create like the same file name, like some marker stand-in file here. This way, if the write files in between or before we commit, we basically like compare the files that we actually wrote to all these marker files that we have and go and delete and clean up the temporary redundant files that have happened. In most cases, it should be like a no op if things are like working fine. But when your Spark job is having issues, shuffle failures, your cluster is going crazy, you can imagine like, this becoming like a large problem. Again, something that you would see with at platform scale, not really with like maybe 1-2 jobs. Then it will become more sufferable kind of problem. Any questions before I hop into the classes?
Nope, just pretty good. Thank you.
Okay, cool. So I think the core classes here are, let me like close all of this. So I think the core class is the table meta client, which you may have seen kind of like earlier. So this one has methods which are essentially going to give you like basic things around. So all of the table metadata we write in this Hudi.properties table, right? So this essentially reads that properties table and it can give you like basic things like what is this a copy and write table, merge and write table. It exposes APIs to query the timeline. It exposes APIs to get the file, file system view, probably not. Mostly the timeline essentially. It essentially gives you APIs to interact with .hudi folders pretty much. Right, anything in the metadata, this is like your like entry point, and yeah, it's pretty much it. It's like it's not a very, it's used everywhere, but it's like a simple enough class. It's not doing too much, and I think all of the timeline stuff is here. There is like yeah, so this is like timeline is an interface. It all sits in this timeline package, and you can see an active timeline. Default timeline just basically is like a shared base class between the two, and there's an active timeline and an archive timeline, essentially, and you have an instant class. You have like these are a bunch of helpers, but most of what you will deal with is all in like all of these state transition kind of things, like, transition this, instant from to this to that. I think that is basic. All of this is essentially here. Like this one class has all of those sort of things. And this is like these two classes now cover the metadata, right? So you want to basically list the, like, get the .hudi folder and then interact with the metadata in there. You want to, for example, um, like the main things that you will find that this class offers you is a whole bunch of helpers, which will tell you, give me all the commits, and then it will just, give you only the commits that have happened. You can only get the cleans that have happened. You can only get the delta commits. You can filter for pending compactions. You can, you can get commits and compactions, like a whole bunch of like helpers, which will all run some kind of filter Java, Java stream filter something on the raw timeline for you. It makes it like consumable for specific purposes, basically. Um, any questions so far?
Nope.
Okay. And then I think the other main class here is the Hudi table file system view. So what the Hudi table file system view is, this actually model, this is like a modeling all the file groups and the actual data, basically, right? So if you, and then it's going to expose, so if you keep looking, going up the hierarchy, this is like a large hierarchy. I'll tell you why. Yeah, this goes all the way here. This is the base thing. This is probably worth looking at. So it essentially gives you for this table, if you list all the files that are provided in a given partition, it basically has a bunch of helper methods which will let you do those things, right? Like for example, for copy and write, if you want to, you know, just if you want to just like, get, okay, let's see. If you want to just get give me all the latest base files, which is, give me the latest base file as of the last committed, um, commit on the timeline. It is going to just like hand you all of that within that partition. And there are two variants of this. So as you can imagine, right, something like cleaner would be interested in all base files, right? But something like writing, it just only cares about the latest. So just to reduce the amount of memory that you have on the driver and all of that, like you just have like a lighter version which only gives you latest. Same thing, slice view is sort of for, this is a superset of the base file only view. You also get to interact with the entire file slices. Yeah, mostly these two were done because for copy and write, we didn't want to use a slice view alone, and then at every point, like, we wanted to have something a little bit more specific and specialized. But yeah, this is going to give you what are uncompacted file slices, like, something like compaction doesn't exist for base file only view, right? So this is essentially giving you file groups on all this like metadata about data for both copy and write and merge and read. And if you keep following this, so the way we implemented the timeline server is, it is one more file system view effectively. So if we can take a quick look at the hierarchy here. Like tomorrow, I think if we were to add our own consolidated metadata as in RFC 15, we will do it that way. So, okay, yeah, so you can see, right? Like, so if you look at it, this is the traditional one, which kind of is updated based on, this is like in memory effectively. There is one that is based out of RocksDB. There is one which is remote. Essentially, all the executors, remember this, like this guy, right? So I said like this isn't the driver, right? The executors, when they call like the remote table file system view. They ask it for the file groups and stuff. It is just a stub and a proxy. It will do a network call within the Spark driver. We will look up the whole like RocksDB file system view, right? So tomorrow, what we are going to do for RFC15, which essentially provides a metadata table inside Hudi itself, so that we don't have to list anything. That will be like one more file system view class that we implement. And yeah, that's kind of like how this part is actually very nicely abstracted. Like you can plug in if you have like some other implementation specific to your thing, you can also add more here. But this is the main, these three classes, if you know, you can actually reason about like more complex parts around, compaction or commits or anything. Any follow-up questions here?
Just quick follow-up question for this. So all the table file system view, are this for the Parquet, the actual data, or this is for the metadata under the .hudi kind of directory?
This is for the data. So table file system view is for the data. The timeline and the table meta client is for the metadata. Okay.
Then in terms of the path, does, let's say when you're trying to reading a Hudi table, right? Does the reader first going to the the metadata timeline, and then getting the latest, let's say the I don't know what's the name, .commits file, and then getting all the active or the latest Parquet files, and then reading accordingly, or it doesn't go through that process at all?
If you can give me like 5 more minutes, I'll get there when we talk to the reader.
Okay.
All right. Thank you.
Thanks.
But if you're clear on the metadata part, like more or less, we can. Oh yeah, and then I want to cover this part, which is all the model classes. So the two main things here, right? So the Hudi common model, it has like models the base file, it has the file slice, it has like all of the file group, there is a group ID, like all of the basic foundational kind of like classes, like Hudi key, Hudi record like payload, all of this is kind of here. And then you can see like, how we describe a file group is it has a group ID, it has a tree map, so it's like sorted by commit time of the file slices, and then it like this is just passed in so that we can do filtering and stuff. But yeah, so each file slice has again an ID, and then like a base instant time has a base file and a sorted set of like log files. Right? So this is like the core thing. This is what all of this file system view, all of this stuff works with. And one more thing, if you're working on merge and read and like, sorry, yeah, here. Right, let me search. Okay, cool. All right, sorry. Yeah, this stuff has all the log format thing. We have our log format actually documented on the wiki page. Maybe we should do it more. Maybe in interest of time, I'll skip this, but it's somewhere here for sure. Let me see if I can quickly find that. So, okay, no mind. So essentially, there's like a log format, and then there's like log format has versions. The log format effectively is like a logical thing where it's like this. You have a base file, and then let's assume like HDFS for now, but none of this really changes for S3 even, except there are no appends. Log format is essentially consists of a file in which we write blocks, right? Each block has a header and a footer and some payload, right? So for example, what this helps us do is, if you want to say, say so some data, so an example of a block could be like a data block. So data block is what we log to the to this when we are doing a delta commit and we in merge and read, right? We are writing essentially, hey, for this base file, we are going to log these updates, right? Or we can be logging like a delete block. So where we just log that, hey, these keys were deleted, right? And data block, we may be writing some Avro data. So we could also be having command blocks, which basically encode things like, okay, look, you remember that delete or data update that we did, that is now rollback, right? So things like this. And then we have an efficient way to, without reading all the payload, we can just skip. We have a skip list where we can like skip through the blocks very quickly as well. And then when a given, so a log file can have multiple blocks, and then a log file reaches a certain size, we will roll that over. But on things like S3, there is no append again, like, so it doesn't, every log append creates like a new log file with one block. That's how it works. But on something like HDFS, you will see that, you actually get appends. So you can have like a small number of log files with many blocks inside. That is all of this code, all of this log way to interact with the log is basically under here. That is more or less the metadata or common classes. If there are no questions, I'll like move on to the right path quickly. Okay. So I want to quickly like summarize what we do in a write pipeline. Meaning like, okay, this is your data frame, right? You want to say observe this, then here are the bunch of things that we do. First, you may have a duplicate keys within the same batch, correct? So we try to like combine those into the same thing. It need not be just deduping. It can be like, it's a general kind of reduce by key kind of operation that you can do. We do that. Then we try to match these incoming records to identify which file groups they belong to, so that we can just go and log to those file groups. And this may be caching, like this index, depending on what you're using. Bloom index, it may be caching, it may be internally shuffle, joining, stuff like that. Then we do the file sizing that I described before. We finally arrive at a partitioning where we decide to send, okay, these are updates, these are inserts, and these updates are going to these file groups. And based on file sizing and all of this, these inserts are going to existing file groups, these inserts are creating new file groups, right? We come to this point, and then we invoke a bunch of classes to actually do the write operations, which is either creating a new base file, logging to the log file, appending to the log file, or like versioning or merging, like creating a new version of the base file. There are only 3 write operations that you can do. Depending on copy and write or merge and read, we just like pick these 3 classes. Then we go back, update the index. For example, if you're using HBase, or tomorrow, when we do RFC8, we do a record level index within Hudi, then we have to go and update the index. And then you commit all of them atomically. Then you invoke cleaning if needed. Then if it's MOR, depending on inline or asynchronous compaction, you either schedule or run the compaction. Then you also do your like archival step, which is moving a few of these older timeline items to the archive folder. So this is like high level, all that happens in the right path. Any questions here?
Nope. Thank you.
Cool. Sweet. So I think going back to the code very quickly, let me close all of this. Hudi write client. is your main thing. Whether you start from your, Spark data source writer, you will start here. You will quickly wind up in Hudi Spark SQL writer or something, which again, if you see, it will just like, sorry, like it will just like ultimately it will at some point instantiate a write client, and then call something like write client dot insert update delete or something. If you look at Delta Streamer or Delta Sync, again it just calls this. Um, that is pretty much somewhere here. Yeah, you will use the write client as well. So this is the core thing, core class. And this is very tied to Spark. There is a PR open, which again we plan to land in 4.6. There's so many things to land in 0.6, which makes this whole thing a little bit more. Give me a second. Okay. Yeah, so this is basic, generalizes this for, Java, like look, like Hudi was written at a, like, or we did all this when there was like the data frame or data set API wasn't even there, right? So I think what we're going to do eventually is to generalize all of this so that it can be like data set or RDD or, like Spark, like Flink data stream or anything else. So that work is going to happen. That's one of the major things that's going to happen to this code base, I think. But overall, I think all of this logic is like upsert, insert, bulk insert. You'll find one operation per this. And if you're curious about when exactly, like say compaction cleaning is triggered, you can look at all of this, right? This is like how we trigger archival. There's a post commit that describes, whether you want to trigger compaction or cleaning or like all of these things. I think cleaning is triggered somewhere here. But yeah, so this is the basic, all of your CLI for save point will ultimately call this. So all of this code will finally call this is all kind of like, this is more like API facade than anything else. All of the different logic for copy and write versus merge and read, all of that is like nicely abstracted here. So there's a Hudi table class. So going back to I didn't catch who exactly asked that question, but going back to the question about what the reader does, right? So what the reader does is essentially it will instantiate a Hudi table. You can see this will tie together the metadata, right? The index, all the writing that is going to happen, and then also the file system view manager. This is who you ask for file system views to be able to query the the file system view. So this is the piece, the higher level abstraction that something like input format will use, or this is what say Presto kind of pulls in Presto DB in their code base as a dependency to be able to support Hudi tables, right? And this has a whole bunch of like lower level APIs, and it's in some cases has like more helper functions, more wrapper, these things, but it'll has these like explicit. I think the more interesting ones are here, which is all the abstract methods, which is essentially saying schedule compaction, compact, okay, bootstrap is something else that's coming up, clean, rollback, and all of this is implemented differently for copy and write and merge and read, right? And like the action basically has one package per action that we support, or one at least like logical kind of like for example, bootstrap isn't really an action, but it's like complex enough that it differs from all the like a commit action, other commit actions. So it has its own like package, but more or less everything else is like a action. And then everything implements this base action executor, which is so it takes a bunch of like common things, and then it takes a result object that it's returning. So most of the cases, this is like, if you're commit, you're returning commit metadata. If you're rollback, you're returning rollback stat, rollback metadata, sorry, rollback metadata. If you're returning like, I don't know, compaction, it's like returning compaction metadata or like compaction plan or something like that. So all of these things do something, do the state transitions and all of that stuff happens within these action classes, and then it comes back with some metadata, right? And through this code, although it takes Spark context, is primarily not like, all it does is uses Spark context for is to do some things like in parallel, essentially distributed execution. That's all. So none of this logic is really very tied to Spark or like any one engine in particular. But this is the core of the actual table execution. And so the other things here are, I think, the main kind of the part that we missed is if you I think in all of these things, right? Something like rollback, save point, restore. These things are more self-contained, if you will, because I mean they're just like more metadata kind of operations, clean, for example, as well. But if you look at like commit or delta commit, they are doing like whole bunch more, right? This is all the code that implements the bin packing and that stuff that we talked about. Like there's code for upsert or inserts or bulk insert and deletes. There are like different code paths for like different sub classes that extend the base at commit action executor. But ultimately, all of the writing, all of the whatever these different APIs are, they will all fundamentally call these three things. Like this is the core. Oops. Okay. Sorry, wrong shortcut. So this is the core of it all, which is the IO handle. This abstracts reading and writing to a given file slice, essentially. So, or file group rather. So if you look at it, these are like fundamentally the different operations. Write is very easy. So you can either append to the log, create a new Parquet file base file, or like version a new Parquet base file, or you can be like getting range information from the base file. You can be just looking at the keys alone for these are all used in indexing, or you can be like just fetching the location for the simple index. So these are abstractions. So whenever you're writing code at a higher layer like table or index, you should just make sure that whenever you're interacting with the base and log files, you're not doing Parquet utils dot blah, but you're going through some read handle and abstraction like this, because this will become like more and more abstracted to deal with different base files and log files. That's at a high level, all the kind of entry point classes that we need to write data here. I think we probably will take a little bit more time to cover index. So probably skip that for now. If are there any questions before I quickly explain the read path role as well?
Just a very quick question. In terms of compaction, you were showing that the interface seems like for compaction is working for both merge on read and copy on write. So merge on read is kind of self-explanatory, but copy on write, like what does the compaction going to do with the table? Is that going to merging the small files or?
No, it's totally error. It's not implemented. It shouldn't be called, basically. So it's just an error so that you don't call it.
Oh, okay.
So compactions are no operator.
Okay, great. Thank you.
Okay. Cool. So let me just at least show you what like at least the basic. If you look at for the reader part, right? I think we saw this before. Let me try to. So this is something to keep in mind, which is kind of when we start on Hudi, we took like um, so if you look at a snapshot, I think we already discussed incremental query, right? So if you look at snapshot query, here's how it works overall. Okay. So step one, it is going to load the active timeline, right? And then it's going to basically create a Hudi table object, first of all, which has its own meta client and all of that. And then it's going to essentially query the commits timeline and say, okay, what is the latest commit time, right? And then it is going to, for all the partitions that the query is interested in, it is going to then, list based on whatever, however Hive is listing today. And then it is going to run that filter through and then all that file system view classes, and then just get the latest file slices along and just pass it on to generating the splits. And then for copy and write, we just use purely the engine's reader. We're using Hive, it uses the Hive reader to read Parquet. We're using Spark, it is using Spark's like whatever vectorize or non-vectorize or native reader, whatever it is. And then if you're using Presto, it's using the Presto reader, right? That was like a pure design goal that we had for copy and write, which was to say, hey, we want to build this file sizing, upsert, delete, all these like other functionality without affecting the query path alone. All we want to do is like do some very lightweight filtering here, and that's how it works. For MOR, if you're doing snapshot query, obviously you do more merging, and then at that point, yeah, we are more responsible for the query performance rather than the engines, because like we still try to use the engines readers for the base file, but our log scanner is ours, right? So that is how overall the read path works. And I know we have like a couple of minutes, but I'll stop here, which is if you look at very simply something like Hudi Parquet file. So you can see we are extending the map reduce Parquet input format, and we are overriding the list where we basically will call super.list status at some point in some of these helpers, I believe. So that maybe you can correct me.
In one of the paths, like for incremental, it's in the list status. Yeah, list status incremental mode, line 95 inside that method. And yeah.
Yeah, exactly. So yeah, so essentially we, depending on the mode, we like whether you're doing incremental query or snapshot query, we essentially have filtering logic here. That's pretty much it, right? Like for copy and write, it's like super simple. For merge and read, like all of this sits in this whole like real-time thing. It's like an aspirational and something that we are building towards. We'll make it a reality, which is all of this like record reader, and then we support like merged or unmerged. Maybe that you just log data because there are only inserts in the log, so you want to not merge but simply read the data. So there are like different options here, but essentially we implement our own record leader and a merge logic in. Or if you're looking for, okay, where do I find the merged the merging code, I think you will.
We want to check for Hudi merged record reader.
Yeah, but I think this got like removed a bit. Yeah, there you go.
Merged.
Yeah, this got moved in. Okay, but anyway, so this is the actual lower level class, which is going to merge and give you like a merge view of the log. We use the base file reader and then merge the base and the log files. And this is where you start looking. If you're interested in Spark, yeah, so inside Hudi Spark, there is like default source. You can see that the code for Spark is very simple. Like Spark snapshot query is very simple. We actually just set a path filter and call like, Parquet, that's all, right? If incremental, we have a separate relation here, which is doing what I described before, which is it is trying to, yeah, this code here is trying to read all the commit metadata in the time range, build the latest paths from which you want to pull from, and then kind of, again, pass it back to with these, predicates on commit metadata time, it just passes it back to this part, basically. That's pretty much what the reader path more or less looks like. We are also doing the merge and read snapshot query in 0.6 for snapshot. So that will give you like something very similar using merge, log record scanner and stuff.
Thank you.
All right.
Thank you very much, Finos.
All right. Thank you.
Thanks a lot.
Okay.
Quick question before this gets shut down. Where can I find an invitation for the Slack channel?
It's there's a tracking ticket, but if you go to GitHub, I think there's like a self sign up link.
Okay. Thank you.
Yeah, thanks a lot, man. Thank you. Bye bye.